So in this video, we're going to take what we learned about with the neuromuscular junction, and now we're going to apply it to a process called excitation-contraction coupling. Basically what's going on is we're using the neuron to excite the muscle to ultimately lead to contraction, okay, which is characterized by the formation of a crossbridge or cross bridges, which is when actin and myosin bind together. So with this video, we're going to start with action potential in the neuron, ultimately leading to actin and myosin forming that cross bridge. And so a quick review, if you recall from both the nervous system as well as the neuromuscular junction, we have an action potential come down the neuron to the axon terminal. And so it keeps coming down, and when it does, it opens up voltage-gated calcium channels. Okay, and that's the voltage-gated denoted by those parallel lines. And so what happens is we have calcium go in to the cell, okay? And we have calcium go in because there's more calcium inside the cell than outside. So as a result, what happens, and we're going to call this 1, and we're going to call this 2, and then we're going to call this 3, what we have is we have exocytosis. And so with exocytosis, we have the movement of the vesicle that contains acetylcholine, and then it releases its contents to the outside of the cell into the synaptic cleft. Now this acetylcholine will diffuse all over the place, but ultimately we're hoping it makes it to this ligand-gated receptor that's on the muscle cell. Now when this happens, this opens up a channel, and in this case it's sodium that can go in. So we have sodium go into the cell, and so that's number 4. And what that does is that activates these voltage-gated sodium channels. And so as a result, even more sodium can go in. So that's 5, okay? This causes an action potential to occur in the muscle cell, and that action potential, which we're just going to denote by these little squiggly lines, goes down. That's number 6. Okay, so we have an action potential that goes along the sarcolemma, which is the membrane, and then down into the T-tubule. And if you remember, the T-tubule they're basically holes that go in the muscle cell so that the action potential can travel down into that action potential, or down into the muscle cell. This action potential will continue going down the T-tubule. It will come into contact here at 7 with what's called the DHP receptor. Now this DHP receptor is a voltage-gated calcium channel. Okay, so we have calcium influx through here. That causes a slight depolarization, but what's probably more important is that when we open this voltage-gated calcium channel, that also opens up a channel on the sarcoplasmic reticulum. So here's my sarcoplasmic reticulum that has a lot of calcium in it. Okay, and so this receptor here, you'll see it abbreviated as Y or RYR. So that's the ryanodine receptor, okay? And so when we open this voltage-gated receptor, the DHP receptor, so right here, that causes, basically there's like a string that's attached to it, attached to the ryanodine receptor, and the ryanodine receptor opens, and then what happens is calcium comes out, okay? And so I'm gonna write down kind of what goes on with each of these steps here, and then we'll take it from where we were just at. So we have an action potential, travels down the axon. So we have calcium influx. This causes exocytosis. I went from 3 to 5, I just noted. Oh no, 4. Okay, and then from what that does is that opens voltage-gated sodium channels. So we have sodium influx, and this is a graded potential. And then we have more sodium influx through the voltage-gated channels, and so now we've got an action potential. Okay, so the action potential travels along the muscle cell. All right, and then from there, it activates the DHP receptor. And once DHP is activated, that does a couple of things. One, we get calcium influx from the T-tubule, and we get calcium influx from the sarcoplasmic reticulum. Okay? And so now we've got a whole bunch of calcium that's floating around inside the fluid, the sarcoplasm of the muscle cell. Now this calcium is important, and I've never figured out how to draw this out, so I'm just going to write it out. But what happens is calcium binds to troponin. Okay? From there, troponin moves tropomyosin. Sorry for all the squeaking. And then ultimately what this does is this allows actin and myosin to bind. So we get actin plus myosin, and that equals our crossbridge. And so from here, what's happened is that just imagine that my fist is myosin, and then just my hand, my flat hand, is actin. Basically what happens is they bind together, and then what happens is that the myosin will pull the actin towards it. It'll let go and it'll grab and keep pulling. It's kind of like a tug of war that we'll just demonstrate in class. But to this point, basically what's happened is actin and myosin have bound together. We've created tension, we've created force, but we haven't started to shorten the muscle cell yet, or the sarcomere yet, and we'll talk about that in a different video. But this is the basics of how excitation, contraction, coupling work.